Hello everybody, and welcome to a new week. Welcome to Ask Math Anything. And I see that some people came here early. That's clearly what everyone's talking about in the comments. Well, I'm very happy to see that you're here, and I'm happy to see that you're interested in asking questions. If you're here for the first time, the way that we work is that people ask whatever questions that they might have, and I try to choose questions that might be understandable to people who are learning algebra or geometry. Now, you will notice that there are sometimes questions that are asked which look like they might take us farther afield. And I always try to choose based on where I think I can tell an interesting story, even if all you're learning is algebra or geometry. And we'll sometimes end up talking about science or other topics. All right, so what kind of questions do we have today? Let's find out. So we usually take a little bit as people start to ask various questions. And I see that some of these questions that are coming are already fairly on the complicated side. We're going to try to find something that will match the general level. Okay, let's do this one. This is a nice warm-up question. This is from Suhas Devarakonda. What's the easiest way to solve this? That's the question. What's the easiest way to solve this? A printer uses 300 digits to number the pages of a book. How many pages are there? $300, obviously. The answer has to be 300, right? Because you used 300 digits. Well, no. As usual, these kinds of things, you need to break it apart into how many 1-digit, how many 2-digit, how many 3-digit, this kind of thing. So let's just try to do this quickly. The question was how to do this efficiently. Usually, if I think about this, I break them into 1-digit pages. And 1-digit pages, there are just 9 of those pages, 1 through 9. 1 to 9, and that will be 9 digits used. Next, 2-digit numbers. How many 2-digit numbers are there? Well, the 2-digit numbers go from 10 to 99. And there are 90 such numbers. One way to see this is because there are 9 ways to choose the first digit, 10 ways to choose the second digit, so it's 9 times 10, 90. But each of those uses 2 digits. So there are 2 times 90, which is 180 digits. Now we're already getting close to the answer. We have 189 digits so far, so let's take 300 minus the 189. Here's my scratch work, always in the upper right. 300 minus 189 is 111. Whoa, what a nice number, 111. So if I have just 111, then I have to divide by 3, right? So the answer should just be divide 111 by 3. That's how many 3-digit numbers I want. 3-digit numbers, I should get 111 of them. And so that's equal to 3 times 111 turns out to be 3 times 37. That's one of these nice numbers. And if you want to just double check, 3 times 7 makes the 21, and 3 times 3 makes a 9, 9 plus the 2 is 11. So that's how you get this. Okay, so that's the answer, right? So the answer looks like there are 37 of them, so it's 137. How many people like 137 for the answer? Now, this is a little bit tricky. This is where oftentimes you make a mistake. Actually, it's very common to make a mistake here. The problem is that the first 3-digit number is 100. Oh, that's so annoying. 100. Now, if I want 37 of these, you see, it's like as if you were counting starting from 0. If you count starting from 0 and you want 37 things, you have to stop at 36. Does that make sense? So that's where this one is, you got to be careful. 136, right? Because from 100 to 136, that's like from 0 to 36. There's 37 numbers there. Okay, so that's the answer. The answer is 136. And that's how I would do this question. And the thing that I always think about whenever I'm doing a problem like this is to make sure I don't make an off by one mistake at the end, because I've done that a lot. And the way you don't make the off by one mistake is you kind of write down like this, from what to what. For me, the 3 dots is like from the bottom to the top. Okay. Oh, and bottom to the top, including the bottom and including the top. All right. What other questions do we have today? Let's see. Maybe people have asked a bunch by now. Oh, I'm curious what the answer to this question is. So this is a question by Daksh Gupta. The product of 2 prime numbers, so the product of 2 prime numbers, I'll just call them primes, okay? 2 prime numbers is equal to 9 more than their sum. 9 plus their sum. I guess the question has to be, it doesn't say what are the numbers. It says, what is the difference between the numbers? What's the absolute difference between the numbers? Let's just say, what are the numbers, okay? I'm curious enough. Let's just find the numbers. If you find the numbers, you can do whatever else you want with them. So, how would we do this? Well, why did I choose this? I chose this because the good thing is, you know when you multiply things, they get big really fast. Like if I multiplied 11 times 13, it's 143. It's huge. It's way more than 9 plus the sum. So what this means is that we won't have to worry too much. The numbers will be quite small. The next thing I like to do is I like to think about odd and even. Because most primes are odd numbers. If you multiply 2 odd numbers, you'll get an odd number. And that could be 9 plus their sum, which is a 9 plus an even number. So that's okay. If one of the numbers was even and one of the numbers was odd, meaning if one of the primes was 2, then the product would be even. But if the even, it still works. All right, so that doesn't help me at all. I was hoping that somehow the even or the odd could help me. But in any case, I don't have to try numbers that are too big, because when you multiply, they kind of get big really fast. So here's what I would do. I would try, I don't want to just guess and check, okay? Guessing and checking is no fun. Let's just give them some names. Let's suppose that my 2 primes are x and y. I have x times y equals x plus y plus 9. Oh, let me show you a neat way to solve these equations, okay? So I know that some people have gotten the answers already, but I'm lazy. I don't want to guess and check. Let me go and subtract some stuff, subtract x and y to the left side. xy minus x minus y equals 9. Now, why did I leave some space? I left some space because I feel like adding 1. I'll just add 1. Why do I want to add 1? Because FFFT. Yes, SFFT. What are you talking about? What is soot? Skylar is apparently talking about soot. Well, SFFT, I think, stands for Simon's favorite factoring trick, after a person named Simon who lives in the San Francisco area and attempts to teach middle school kids graduate level mathematics. He's a really interesting guy. But now let's go over, he's actually a really interesting guy. Now let's go over here. What are we supposed to do? Well, we can start factoring. Look at this. Take the first 2. The first 2, that one I can factor out an x. X times y minus 1. Oh, gee. This thing looks a lot like y minus 1, just minused. So I can say minus 1 times y minus 1, and that equals 9 plus 1 is 10. Okay, let me stop for a second. How many people think this makes sense? All I've done is I started with the equation, xy equals x plus y plus 9. Then I said, let's go and subtract the x and y over to here. Okay, fine. And I just want to add 1. The reason I want to add 1 is because I want to be able to do this. Now, once I have an xy minus x and a minus of a y plus 1, now it's called factoring by grouping. That's actually what I call it. But this is like an x times the parentheses y minus 1. That is xy minus an x, right? And then over here, magically, because I put the plus 1 there, that's why I did that. I put the plus 1 there so I can make a y minus 1 chunk. Okay? Because I already saw this minus y, this minus y I would put here, and I want it to be y minus 1, so that's how I knew I should put a 1. Okay? Now, let's factor again. I have a y minus 1 and I have a y minus 1. Pull those out. if you pull those out, you get x minus 1 times y minus 1 equals 10. Ah, now the game becomes, can we factorize 10? And if we factorize 10, that would be something times something, right? And this makes life so much faster. How do you factorize 10? Well, obviously the way you factorize 10 is you say it's 2 times 5, right? Maybe this guy is 2 and this guy is 5. Could that be? If x minus 1 is 2, what's x? 3. That's prime. That's okay. If y minus 1 is 5, what's y? 6. Oh no, that's not prime, so it doesn't work. But then you say there's another way to factorize 10. The other way to factorize 10 is 1 and 10. Now if you factorize 10 by 1 and 10, then you say if x minus 1 is 1, then what's x? 2. And if y minus 1 is 10, what's y? 11. So now I see two primes, 2 and 11. And they work. So you can double check it. If you take 2 times 11, that's 22. And the sum of 2 and 11 is 13. 13 plus 9 is 22. Ah, now we have some more questions. P14Y3R0N3 asked, can there be other answers? Oh, Daksh Gupta, yes, you're right. That's not the answer though, because the question you asked me was what is the absolute difference between the numbers? The absolute difference between the numbers is then 11 minus 2, which is 9. However, I wanted to go and ask the general question to everybody to say, hey, how can you find them? Okay? And now let's answer the question of, are there other solutions? Well, how else could you factorize 10? Right? If I want to have prime numbers x and y, then my prime numbers x and y will be integers. But furthermore, if you take any prime number minus 1, that's still going to be a positive integer. So if x and y are positive if x and y are primes, then that will give me a factorization into two positive integers that multiply to 10. And the only way to factorize 10 into positive integers is 1 times 10 or 2 times 5. You can also do it with 5 times 2. But 5 times 2 will just give you the numbers flipped around. And not 11. And 10 times 1 will also just give you the numbers flipped around. 10 times 1 will give you 11 and 2. So actually we've now proven that this is the only solution with two prime numbers. The reason I wanted to do this is because guess and check takes too long. Why would you want to guess and check? What if the problem was worse? You can do this actually in general, even if the problem doesn't have a 9, but something else that's like bigger. And all you have to do is factorize the right-hand side. All right. Well, thank you everyone for following along with this. This is actually a pretty tricky trick, but I think it makes sense. Hopefully it makes sense to as many people as possible. More questions. What do we have? Oh, Keshav says we could have gotten to this instantly by using the fact that 1 prime has to be even. How did you know that 1 prime has to be even? I think I'm a bit slower than you. Because when I look at this, I'm like, in theory it could be odd, right? Because if I have two odd numbers multiplied together, I could have an odd thing here. And if I take two odd primes and add together, I get an even number plus 9 is an odd number. So I don't see how I have a contradiction, right? If I had odd and odd, the left side would be odd, and the right side would be 9 plus even, which is also odd. So I actually don't know how to right away say one of the numbers has to be 2. That's not clear to me. Nevertheless, that was what I was hoping. I was actually hoping from the beginning I could just use that and finish it, but it didn't work. Yeah, I actually don't get why one of them has to be even. Maybe you have another way of seeing it. If you have another way of seeing it, please share. But, oh, I see. Well, we know why one of them has to be even by doing it this way and saying I'm factorizing 10. And if you factorize 10, then you can see it. But if you don't do it by factorizing 10, I don't exactly know how you do it just by looking up here. Okay, more questions. Oh, Shuang Lu has asked a very, very deep question. Shuang Lu wants to know, what is the difference between pi and phi? It's an H. I think you meant as mathematics terms. Okay, so somehow it's not just an h. Pi, we know what pi is. Pi happens to be a Greek letter, and it's this circumference divided by the diameter. Circumference divided by diameter. And that's approximately 3.14. And more stuff. 1, 5, 9, 2, 6, and some stuff. Now phi is something else. Oh, I should go and use yellow. Okay? So yellow is for phi. Phi, by the way, is another Greek letter. It's written like this. Sometimes people write phi a different way. You might see phi written this way. These are both phi. It just depends on how you want to write down this Greek letter. But both of these are legitimate Greek letters. Okay? And now, what is the phi? Well, these are the golden ratio. They're the same thing, by the way. These two are the same thing, and the reason I use the golden color is because these are the golden ratio. Golden ratio is the ratio between the length, oh, that's probably not quite right. It's like the length and the width of this very beautiful, let's make it more beautiful. That's more beautiful. This is a very beautiful rectangle, okay? This is a very beautiful rectangle, and it's the ratio of this length divided by the width. Now, there are all these different ratios. As somebody said, remember silver ratio? We talked about that also on this live stream. But so, you know, this is golden ratio. We talked about these a lot here. If you're curious, you can look up more. It has something to do with beautiful ratios. And just as another fun thing about the golden ratio, if you actually draw a 5-pointed star, the golden ratio also comes out here. The golden ratio also happens to be, I think it's the same as the ratio of one side, the long side of this triangle, to the short side of this triangle. I think. I'm trying to think. You know what? Since I'm curious, let's go and double check that, okay? I think it's actually the ratio of the long to the short. And we're going to double check that, I think. But I'm not happy just saying I think. And I mean, I'm sure you can Google it, but it's more fun to figure it out. So we'll figure it out in a second. But what this golden ratio is, the golden ratio is exactly 1 plus square root of 5 divided by 2, and it's approximately 1.618. But now, since you got me thinking, I want to go and figure out what's going on with this 5-pointed star. Okay? And yes, people are saying there are maybe other kinds of ratios. The golden ratio is the most common one, the most interesting one. So, let's go and figure out what's the deal with that 5-pointed star, because now you've piqued my interest. Now, a 5-pointed star, I'm going to do some geometry. Let's pretend that's sort of an okay star. It's not really that good. This guy is kind of a midget compared to that guy. But let's pretend that they were all the same size. It's actually really hard to draw these because if I try to draw without taking my pen up, there's no way to erase part of it. So you actually have to go and draw the entire thing. But let's talk about some angles. All right, this actually is like a problem we talked about earlier in another one of these live streams. I think it was the Knights of Pi Math Tournament collaboration. But does anyone know anything about angles in this picture? So there are some angles. Some angles are the inside angles of these pentagons. Oh, well, of the pentagon. There's only one pentagon. Oh, let's not do that one. Let's do the exterior angle. That's even better. If I happen to have any shape, like a pentagon, like this. The exterior angle means I take this thing. I could look at these exterior angles. The sum of the exterior angles is always 360 because it's sort of like you're crawling around and it's like how much you've turned and how much you've turned and how much you've turned, and eventually you turn 360 degrees all the way around. So the sum of the exterior angles is 360. Because the sum of the exterior angles is 360, if it's a perfect regular pentagon, then each of those is 360 divided by 5. What's the easiest way to take 360 divided by 5? The easiest way to divide by 5 is to divide by 10. Oh, just kidding. But that's wrong. You want to divide by 5. So you divide by 10, and then you times 2. Right? If I want to divide by 5, it's the same thing as 360 divided by 10 times 2. Now that's easy. That's 36 times 2, that's 72. It's somehow easier for me to double a number than to multiply it by 5, or divide it by 5. So now I have 72. That means that each of these triangles, let me draw this one since I have more space, because this is a bigger lump. So each of these insides is 72 and 72. So what does that make this angle? Well, this is using just like the sum of the angles in the triangle. The sum of the angles in the triangle is 180. So whatever this is 180 minus 72 minus 72, which is equal to 180 minus 144. 72 plus 72 is 144. And that's nice. 180 minus 144 is actually 36. Okay, so now I made a claim. My claim was that the ratio of the long to the short was nice. How would I figure that out? Let's do this. I'm going to draw another picture, and the other picture is just going to be a blown up version of the 72, 72, 36. I have to blow this up. Woo, big. That's too big of an angle. Darn it, this is actually really hard. That's too small of an angle. Maybe that's just right. This is close enough. 36, 72, 72. Okay, I claim that somehow the ratio of the long to the short is interesting. And here is a trick. I'm going to take this small angle, not small, I'm going to take this big angle here and cut it in half. Zoop. Oh, I cut it in half. That means this is 36 and this is 36. Now, why is that exciting? The reason that's exciting is because, hey, it's another 36 and a 72. Similar triangles, Daniel Wu, you're right. If I have a 36 and I have a 72, can you tell me anything about that angle? We've seen this before. 36, 72 gives you 72, right? That makes sense. Should have a 72. Oh, now I have some similar triangles. That means that the ratio of this piece to this piece, well, let's put some numbers first, okay? Let's do this. This whole thing I'm going to call 1. The reason I'm calling this 1 is because I'm curious what this is. I'm calling it x. Why did I do that? The reason I put an x and a 1 is because I want to know what is x divided by 1. Okay, my whole goal is to find out x divided by 1 is what? Because I made some bold claim while I was talking about the golden ratio. I told everyone, hey, that long thing over the short thing, that's the golden ratio. And then I caught myself and I said, oh, I'm not sure. I don't know if that's exactly right, so let's double check. So now I want to know, what is x? Once I find x, that is this ratio, whatever that may be. But now why did I do that? The reason I did that is because there's also some isosceles triangles here. See this one? What's the length of the blue thing? And why? What's the length of the blue thing and why? One, also 1. And why? The reason why this one is also 1 is because of base angles theorem. Because look, 72, 72. So this thing here is an isosceles triangle. 72, 72 means that this side and that side are the same length. So that's a 1. That was exciting. So like for doing almost no work at all, I got another 1. Now why is that exciting? The reason that's exciting is that there's a 36 here and there's a 36 up there. So now if I have a 36 down here and a 36 up there, well, I think that means that this is equal to that, right? I've got another isosceles triangle, even if it doesn't quite look right in this picture, right? I've got 36, 36, so that the opposite sides are the same length. So I have a 1 here. This is 1. Why is that useful? Oh, the 1 looks like it's running into my arrow. Let me draw the arrow again. Why that's useful is because I can now say what is this length. The reason I know what is this length is because the whole thing was isosceles. If this guy was x, then this thing here is also x, right? Because I had 72 and 72. So if that was x and this whole thing is x, then what is the leftover bit? It is x minus 1. Thank you, everyone is on this. I like this. So this is x minus 1 for this part. Finally, we use similar triangles. You see, this small triangle here has the same ratios as the whole triangle because its angles are the same. I mean, the angles correspond. The big one was 36, 72, 72, which means that if I just kind of tilted it and then shrunk it, I'll get this one, 36, 72, 72. So then the ratio of the long side to the short side of the small triangle is the same as the ratio of the long side to the small side of the big triangle. Ratio of the long to the small is the same. The small triangle gives me a ratio of long. What do you mean long to small? Should be long to short. We don't do long to small. Long to short is the same. And now let's do the same thing. Now let's use it, right? The one which is the big long to short is x over 1 is equal to, for the small guy it's 1 over x minus 1. Okay, now let's solve for x. Multiply, multiply. So multiply by x minus 1. X squared, yikes. X squared minus x equals 1. So that's x squared minus x minus 1 equals 0. Use your favorite way of solving quadratic equations, and you get this plus or minus this. Minus 4ac is a 1 plus 4 all over 2, which is equal to either 1 plus or minus the square root of 5 over 2. But it can't be minus because that would be a negative number, and that's not a length, okay? So you could get rid of it. So, but it's not minus. And that finishes it. So I was right. So it actually it is indeed the golden ratio, 1 plus root 5 over 2. The golden ratio is indeed this over this. And that happens to be in any 5-pointed star. So if anyone ever asks you, can you get the golden ratio? Just draw a 5-pointed star, and the little lumps that stick out on the end of the 5-pointed star are going to be giving you that golden ratio. And this has a name. This is actually called the golden triangle. Okay. More questions. Oh, Daksh Gupta has asked, is there a name if I use the negative number? What should we call that? 1 minus square root 5 over 2. I have a suggestion. This thing could be wrong. I could be horribly wrong. Am I wrong? I don't know if I'm wrong. I'll find out soon. I could be wrong. So I think that the negative number is something like minus 1 divided by the golden ratio. Let's try. Okay, so the golden ratio is 1 plus the square root of 5 over 2. Daksh Gupta has asked, what if you decided to be a weirdo? What if you did 1 minus root 5 over 2? Is that nice? Here's a claim. Well, I'm going to see if it is or not. Is it minus 1 over the golden ratio? Let's find out. I'm not sure if this will work, okay? So let's just go and find out. The opposite of gold is trash. So this is the trash ratio. I mean, I could be wrong. Let's go and try to figure out what this is, okay? So if that was this golden ratio of phi, let's go and try to figure out what would happen over here. Okay? Let's see. If I'm over here, I guess I should just try to take 1 over the phi. Okay? Let's go and find out. Let's just take 1 over the phi, and then let's take a minus of it. So the way I would check this is I would say, well, first, what is 1 over golden ratio? That's equal to 2 over 1 plus root 5. Oh, actually, I care about minus of it. So minus of it is minus this. Oh, I mean, of course, this is bogus. Like, how could this be equal to that? It's just like, no way, right? Like, this thing equal to that? They look so different. Well, let's try to mess around a little bit. So this thing happens to be minus of 2 over, I'm going to write it as square root of 5 plus 1. I haven't changed anything yet. And now I'm going to do something called rationalize the denominator. The way you rationalize the denominator is you multiply by a fraction, and the fraction has to equal 1. And I'll use root 5 minus 1 over root 5 minus 1. Okay? Now, why am I doing that? Why did I choose to multiply by root 5 minus 1? Well, first of all, that's just 1, so of course it's equal. I had the old thing times 1, okay? And now if I look at this, why did I choose root 5 minus 1? Well, because if I multiply root 5 plus 1 by root 5 minus 1, this is called a difference of squares. Something plus something times the first thing minus the second thing is the first thing squared minus the second thing squared, if you try to expand it out. Let's do the top first. I get minus of, well, let's do this. I have minus of 2 times the square root of 5 minus 1, yikes, minus 1, divided by, now let's do it. Root 5 times root 5 is 5. Root 5 times minus 1 is minus root 5. But then I plus a root 5, so those cancel, that's fine. And then I have minus 1. Oh, it looks like I need to do some arithmetic. Well, okay. 5 minus 1 is 4. 2 over 4 is a half. And the minus sign makes me flip that thing. Okay, so what actually happened was I have 2 times 1 minus root 5 over 4, which looks like 1 minus root 5 over 2. Whoa! It's the same thing. Huh? How come it worked? That's kind of interesting. So how did it work? Why is this possible? Because also somebody else told me, no, this is stupid. What do you mean minus 1 over 5? There's something else you told me. You said, no. It's actually not that. You said it's something like 1 minus 5? People told me, if I want to know what this thing is, just take 1 minus the golden ratio. Oh yes, what's this 0 with a slash? This is the golden ratio. We just did that. The golden ratio is this number, 1 plus root 5 over 2, and this funny symbol is a Greek letter. The Greek letter is called phi. Okay? And the golden ratio we just saw was something that comes from 5-pointed stars. It's something that comes from beautiful rectangles. And I mean, this 1 minus of this thing is very clearly that thing. Right? I'm okay with that. Like if I took 1 minus of this, I would get a 1 minus a root 5 over 2. So now here's a question. Is it surprising that 1 minus phi is the same as minus 1 over 5? Why? Well, think about it this way. If I have 1 minus phi and I have this 1 over phi, minus 1 over phi, I can write it like this. So, apparently, they're equal. But actually, if you look at this, and if you multiply up by a phi, and divide down by a 1 minus phi, this is sort of the same equation, except for these divide by 0 things, but the phi is not 0. This is sort of the same as phi, is it equal to minus 1 over 1 minus phi. Okay, but now that is definitely the same thing as comparing phi to see if it's the same as 1 over phi minus 1. And hang on a second. You see this equation? This equation is pretty familiar. We just saw this equation. That was here. X equals 1 over x minus 1. Phi equals 1 over phi minus 1. So in fact, they're the same. So that's actually why all of these are the same. It's okay to write it as 1 minus phi. It's also okay to write it as minus 1 over phi. And that's the golden ratio. I saw that there are some people here who maybe haven't taken this part of algebra before. And so we'll move on to another question. And hopefully that one will be even more understandable to more people. Okay. So the answer about the difference between the phi and the pi is that one of them measures circumference divided by diameter. The other does something with these like beautiful 5-pointed stars. More questions. I see that Moonwatcher123 asked, did you know that bananas can come in different colors, like red? Yes. But again, the reason I know that is because down the street from this studio where we film is a Mexican grocery store, which is full of all different kinds of bananas. we also, in the same store, that's also how I came to learn that there are many, many different types of peppers, chili peppers. I mean, I've been used to like red chili peppers. But if you go and check out the people, like all the different peppers that are in the Mexican store, the Mexican grocery store, it's like, wow, there's so many different kinds of chili peppers in the world. Okay, now let's see, what else do we have? Oh, let's try this one, okay? So this one happens to be by Unknown Monkey. And Unknown Monkey has a problem about the sequence. The sequence goes 2, 6, 12, 72. Hey, does anyone know what's going on in this sequence? Does anyone know how you get the next term in this sequence? It looks like if I go from 2 to 6 to 12 to 72, then if I want to know the next term, I see this x. It's like multiply, right? That's all that's going on here, right? I just do 2 times 6 is 12. 6 times 12 is 72. 12 times 72, yikes, it's something big. What is it? That's kind of hard. 12 times 72 is 720 plus 144, which is 864 maybe. Oh yeah, it's 864. But I'm not sure I want to do the next one. So it's going to keep going and going. And we have this awful question. The 9th term. Oh no. The question is, what's the 9th term? Fortunately, the question doesn't say write down the 9th term. The question says the 9th term happens to be 2 to the power something times 3 to the power something. And the question is, what are those somethings? The question actually asked, what's the sum of those somethings? But let's just ask, what are those somethings? Aha! So for these kinds of problems, if I look at this, it's a lot easier to think of it by factoring. So what I'll do is I'm going to make a table. And the table is going to have, let's call it the power of 2 and the power of 3. Maybe let's call it the exponent. Well, let's call it power. That's about the same. The power of 2 in the answer, the power of 2 in the 2, and the power of 3. Does my table make sense? I'm going to say, what's the power of 2 if I just have 2? Well, 2 is just 2 to the 1 times 3 to the 0. So if you see, I wrote this chart. If I have a number 2, that is 2 to the 1 times 3 to the 0. Okay? How about the 6? Can someone tell me what two numbers to write here? What's the power of 2 in the 6? And what's the power of 3 in the 6? Pow for power. That's right. Pow. Okay. What is the power of 2 in 6? Yes, thank you very much, Dr. Gupta. It's 1 and 1. And that's because I have 2 to the power 1 times 3 to the power 1. Seems reasonable. How about the 12? Can anyone tell me what's going on in the 12? 2 to the what times 3 to the what? Thank you again, Dr. Gupta. 2 squared times 3 to the 1. How about the 72? Who is good at factorizing numbers? 72 is 8 times 9. So if it's 8 times 9, then yes, it's 2 cubed times 3 squared. And I already see that somebody said, wow, these are the Fibonacci numbers. You know why they're the Fibonacci numbers? It's because if I multiply together two of these, what happens to the powers? They add. Yes. What's the question? Andy Jia asked. The question is called, I've got 2, 6, 12, 72. Those are the first 4 terms. And we want to know if we go down to the 9th term, what are these two numbers? That was the question. Okay. Oh, this is a national math counts problem. That's exciting. You know what? Actually, I'm now going to even say the real question wasn't what are these two? The real question was what is the sum? The real question wanted to know what's the sum of the powers. So let's do something else on this chart. Whoa, that was too far to the top. we also want to know the sum. Hey, you know what these sums are? 1 plus 0 is 1. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. Oh my gosh, look at those sums. The sums are Fibonacci. You know why? It's because first of all, each of these are Fibonacci. If I multiply together two things, then if I get the next one, the power of 2 is going to be the sum of the powers of 2, right? If I multiply together numbers, then the powers add. 2 to the 1 times 2 to the 2 is 2 to the 1 plus 2, 3. So I've got Fibonacci. Then I've got another Fibonacci. And it just so happens that the Fibonaccis are like, they're lagged. Since we're all talking about lag on YouTube, I'm going to say that, man, these are lagged. This particular column has lag. It has a lag of 1. And the reason this has a lag of 1 is because it starts from 0 and 1. And since it has a lag of 1, then when I add across, it's sort of like just adding together two Fibonaccis that are right next to each other. So that's why the answer is always going to be a Fibonacci number. And now, I see, somebody else, P14, Y3, R0, and 3 said, or maybe the first column is just, I am speed. It could be. Either this one is speed or this one is lag. Doesn't quite matter. When you add them across, you get Fibonacci's. And so now I just want to know, what's the ninth thing that's going to happen here? I already have 4, so let's just Fibonacci our way through. I need to know the ninth thing. 1, 1, 2, 3, 5, 8, 13. Yikes. 13, 21, I can't count. 34. How far are we so far? Do we have 9 things yet? Oh, counting is so hard. No, not yet. Is it? No, not yet. Yes, 55. Ooh. I'll make a guess for 55. But I see people said 89. So maybe I screwed up. It's 89? What happened? Okay. 1, 2, 3, 5, 8, 13. What just happened? So we want the 9th term. Honestly, my counting skills are very weak. But I think that's actually the 9th term. I think we're okay. Like what I just did here is, I just added all the way down. And because I happen to know the Fibonacci numbers reasonably well, because you just see the Fibonacci's all the time, once you see it's a Fibonacci pattern, you just go 1, 2, 3, 5, 8, 13, 21, 34, 55. And the hardest part is like, do I have 9 numbers yet or not? Okay. Well, I hope that's the answer. I think this is a really neat question, and thanks for sharing that it came from National Math Counts. Those guys do know how to make good questions. Ooh, you asked, so is the sum 10? No. The sum is actually 55. This is legitimately the answer. The question was, the 9th term is 2 to the power something times 3 to the power something, and the question was, what happens if you add together those powers? And that's why what we did is we just did a bunch of the terms, and we saw that the powers are 1, 0, 1, 1, 2, 1, 3, 2, and then we saw what happens when we add. If I did 1 plus 0, it's a 1. 1 plus 1 is a 2, and so on. So then I get all these Fibonacci's, and this column is actually the column of answers, where the answer is the sum of the powers. All right. More questions. Take a sip of my water while I go and choose some questions from the chat. What is this? Vera Wang, you're so funny. What's the difference between the Po-Shen Loh ratio and the daily challenge ratio? I'm not entirely sure how to answer that question. But let's consider the difference to be 0, because somehow both of them are done in the same way. How about that? Okay. Moonwatcher 123. If you had to eat one, which? Crispy apple, savory popcorn, or sweet energy bar? What's a crispy apple? Do you just mean like an apple, which happens to be crispy, or is that some kind of a snack food? I would actually probably go with either the apple, if it's a legit apple, as opposed to some weird snack. That sounds like a reasonable thing. The sweet snack energy bar, or whatever you said, that also sounds reasonable if I was particularly hungry. More questions. What? Why are you asking me all these puzzles? Now I'm curious. Moonwatcher 123. 5 plus 5 plus 5 equals 550. And you're saying that we get to draw one straight line and we have to make it true. Draw one straight line to make true. I mean, yes, my answer would have been, am I allowed to just do that? That would be my answer, but I'm not really sure if this is allowed. I'm not sure if you wanted like a more fancy straight line. I'm not really sure I see any other way to do this, but I think that's what I would do. If this is not the answer, and if you have something else in mind, please let me know. Okay. Oh, it is. So that's the answer. All right. Very clever. More questions. Oh no. Another puzzle. So we seem to like these puzzles. So do I. They're quite creative. This is by Daniel. You're telling me that 5 plus 3 is equal to 28. And you're telling me that 9 plus 1, is this one of these broken calculator questions, is 810. And 8 plus 6 is equal to 214. And 5 plus 4 is equal to 19. What is 7 plus 3? Broken calculator. Oh boy. Well, let's see. As I was writing all these down, I said, some of these numbers are ringing a bell. Like whenever I see 8 and 6, the thing that pops into my head is 14. And there's a 14. And 9 and 1, there's a 10. Oh, this is maybe not bad. So what looks like is happening is that there's an 8, there's a 10, there's a 14, there's a 9. Those look like the sum. And how about the first thing? The first thing looks like the difference. It looks like it's 5 minus 3 is 2, 9 minus 1 is 8, 8 minus 6 is 2, 5 minus 4 is 1, 7 minus 3 is 4. And 7 times 3 is, no, not times. 7 plus 3 is 10. And we're good. Okay, that was fun. I mean, in this case, maybe it was not as hard, but you never know. Actually, whenever I look at these things on the chat, I'm like, wow, what's here? Let's go and start writing stuff down and see what happens. More questions. Oh, let's try this. This is crazy. This is a question by Jenny. And Jenny says there's a magical truck. Well, Jenny didn't say it was a magic truck. Jenny just said it's a truck, not a trunk, a truck. And this truck I consider magic because in the xth minute, so truck goes at 2 to the power x miles per hour in the xth minute. And how far does it go in 1 hour? So how many miles in 1 hour? How far in 1 hour? Oh, how bad could this be? Oh, Temp ID says the driver is drunk. Implicit says truck go brrr. In fact, as people know, outside my office, there are a lot of people who like to drive really, really fast. So it could be that one of these people is driving this truck, which goes at 2 to the x miles per hour in the xth minute. Now, I will say, this is pretty impressive, Do you realize how fast this person is driving in the 60th minute? In the 60th minute, this truck driver is going at a speed of 2 to the power 60 miles per hour. 2 to the power 60. How big is 2 to the power 60? This is just for fun, okay? How big is 2 to the power 60? Well, something I often like to do is 2 to the 10 is a nice number. So we'll just do that, okay? Those are equal. 2 to the power 10 times 2 to the power 10 times 2 to the power 10. This is fine, okay? And so this happens to be 1024 to the power 6, which is approximately 1,000 to the power 6. Yikes. And 1,000 to the power 6 is equal to 1,000,000,000,000,000,000,000,000. Oh no, it ran into my head. 000. like that. That's kind of fast. Oh, is right. That's just like so fast because the speed of light is like 300 million meters per second. And if you try to convert speed of light into miles an hour, which I actually don't really know because I never think about it in terms of miles an hour, but it's the same order of magnitude, this is actually faster than the speed of light. That's why I'm saying this truck is insane. The speed, this truck is eventually going at illegal speeds. Oh my gosh, it broke the speed limit. This truck breaks the universal speed limit. It should get a massive ticket. Because it didn't just break the speed limit of like 55 miles an hour in the United States. It broke Einstein's speed limit. Okay, anyway, let's just go and assume it's possible, okay? Assume it's possible. Now, how do you do this? Oh, you're asking, how do you define speed at an instant? I think the person asking this question was not really thinking about speed at an instant. They were just like, you know, for this entire minute, the driver is going at that fast, and then the driver jams on the gas and goes even faster for a minute, and then goes even faster for a minute, and so on. But yes, if you actually want to do this problem, it's not that hard to do it in theory. It's that somehow if you're going this many miles per hour for 1 minute, then what you can say is in the first minute, what you did is the distance you've gone is 2 to the power 1 times the number of hours, right? It's 2 to the power 1 miles per hour for 1 minute. That's how many miles you've gone. And in the second minute, you go 2 to the power 2 times 1 over 60. And so this keeps going. This keeps going all the way down to the 60th minute, which is 2 to the power 60 times 1 over 60. And there's a nice fact, which we don't have time to do here to explain why, but if you add up all of these powers of 2, 2 to the 1 plus 2 to the 2 plus 2 cubed and so on, all the way to 2 to the power 60, the answer is nice. If you add all this together, it's like, maybe you've noticed this before. If you add 1 plus 2 plus 4, it's just 8 minus 1. 1 plus 2 plus 4 plus 8 is just 16 minus 1. Okay? So if you go and add all these together, it should be, you're just adding up powers of 2, right? So it should be 2 to the power 61, the next power of 2, minus not 1, but 2 times 1 over 60. And the reason why it's minus 2 is because if I go and add up the powers of 2, starting with 2 to the 1, that's like 2 plus 4 plus 8, and so on. But it's actually 1 plus 2 plus 4 plus 8, which is 16 minus 1. So anyway, that's why I go to the next power of 2, minus 2. And you know, we could simplify this if I wanted to. Yeah, part of me wants to simplify it. I'll get 2 to the power 60 minus 1 over 30. And that doesn't simplify anymore. Actually, does it? Well, 30 has powers of, not entirely clear, but I'll say even if I could simplify it, it would look worse if I tried to actually divide out the 3 or the 5 from here. Okay, so unfortunately, the answer is huge. Also, unfortunately, it's against the laws of physics. Xiaolin Wang asked, would the truck burn up? Well, no. Actually, what happens is you just can't get any faster. And there are certain things about, oh gosh, I forgot my special relativity. It's been a long time since I've learned that. There are certain things that make it hard to move close to the speed of light. So I'm not entirely sure I remember what makes it so difficult. If I remember correctly, does your mass change? I don't quite remember. It might be that your mass suddenly changes, or what's going on, not suddenly, continuously. It might be that as you're going faster and faster and you keep pressing the gas, you actually don't get much faster. It's harder to get faster the faster you're already going. Yeah, your mass gets huge. Oh, thanks, Ron Yoder, you're here. So my memory was that somehow your mass gets bigger, because I remember that in relativity, there's a notion of a rest mass. And the rest mass is like if you're still, how much is your mass? But as you're getting faster, your mass gets bigger. And as you push the gas, the way that acceleration works is that there's a physics thing. You have to put some force there. And the acceleration is like your force that you put divided by the mass that you have. So if you have more mass, the same amount of force doesn't make you much faster. So anyway, that's relativity for you, and so that's why you're just not able to keep jamming on the gas to go faster and faster. Yeah, Vera Wang is sort of right, because your mass gets bigger, it slows you down. Not quite. Actually, what I'm saying here is that if your mass is too big, when you try to press the gas, you don't get as much extra oomph. The way to think of it is like this. You know, we can exert a force, right? If I push, and if I use all the force in my hand, and I push like a baseball, I can make a baseball go really far. The baseball has not that much mass. I know some people here are complaining, why are we talking physics? Because physics and math are connected. But see, now let's suppose I use the same amount of force to go and push a car. It's a little bit harder. But I mean, if the car was in what's called neutral gear, and if it was flat, I could probably still push it. But you know, it wouldn't make the car go as fast as I can pitch a baseball. Now imagine that it wasn't a car. Imagine it was like a tank. I'm just saying like something really, really heavy, still in neutral gear. You try to push, and it would be really hard to push. So the point is, the more the mass is, the same amount of force that you try to make makes less acceleration. It doesn't cause it to get as much faster. So actually what's going on if you try to press the gas while your truck is starting to accelerate close to the speed of light, the closer you get to the speed of light, the bigger your mass becomes, and the harder it becomes for you to get faster. And that's actually why it's impossible to pass the speed of light. TempID asked, how much engines does this guy have? That's a good question. Yeah, fun question. We have a few minutes left. What can we do? P14Y3R0N3 asked, are all the roads in the world even that long? No, almost definitely not. So, yes. So let's keep going. Ooh, Daksh Gupta gave us a puzzle. Can we actually finish this puzzle in like 3 minutes? Let's try. I need all your help because this might be too hard. Use 8 8s to make 1,000. To make 1,000. And you can use addition, subtraction, multiplication, division, exponentiation. That looks like a weird division sign. Exponentiation, factorials, and square roots. All right, how can we do this? Let's try to do this. We get to use 8 8s. So we could try to, apparently you cannot mash numbers together, okay? Oh, you can. You can also mash them together. Can also mash. Okay, well, I'll tell you what I would try to do. I'll try to mash first, okay? Because my attitude is if I have 8 8s, let's go and get things like reasonably big first and then figure it out later. So if I had 888 plus an 88, that's using 5 of them so far. That gives me 8 plus 8 is 16. 8 plus 8 is 16, 17, 9. Ooh, that's close. So if I have 976, how much more do I need? I need 24. Oh, it works. Okay, I saw some people also say this. It works. Because if I just take 888 plus 88 plus 24, which is 8 plus 8 plus 8, that's equal to 1,000. And we managed to make it before the time ran out. Okay, thank you. It's actually not that bad. I was not sure because you gave me all these things I can play with, so I thought it might be messy. Thankfully, we have a lot of people here who are pretty sharp. Okay, and we already did this riddle? Oops. Okay, in that case, we already did this riddle. What else do we have here? Oh, that's really neat. Vera Wang asked, what's the max distance between 2 watchers of today's AMA? Well, usually we happen to have people who are watching this from India. And so if we have people who are here from India, then the distance becomes something pretty serious because now we're able to almost go through a good chunk of the Earth. And, you know, I might just guess. We happen to know the radius of the Earth is about 6,000, what was it? 6,000 miles? I already forgot now if it was miles or kilometers. But suppose it was like 6,000 miles? Or no, but I think that was kilometers. Anyway, let's just say if we've got 6,000 plus another 6,000, I'm going to guess that the distance might be something on the order of 8,000, 10,000 kilometers, something like this. Oh, miles. Yes, kilometers. So I switched it to kilometers. But pretty serious, because we happen to be able to probably have the distance from somewhere in the United States to somewhere in India, which is fun. And I'm really happy that you guys are still watching from India. 12,000 give or take 1,000. Oh, yes, Simon Miller, you are right. Why do you always put it this way? So, yes, aliens could be watching. And if aliens are watching, then in that case, the distance could be quite far. But not more than 1 light hour, because the speed of light is how fast light can travel. And the waves that come, the information that comes from the Earth travels maximum at the speed of light. And therefore, since the beginning of this live stream, the farthest away the aliens could be to still have heard this is 1 light hour, the distance it takes, the distance that light can travel in 1 hour. Now, 1 light hour doesn't quite get you to the next solar system. So, actually, the aliens don't know yet. Unless there are some aliens who are able to receive radio signals who are somewhere in our solar system. Maybe they're listening to us on the asteroid belt. But I think that's beyond the scope of today's live stream. And thank you to everyone for coming today. Hopefully you had some fun. We'll be back again tomorrow with another round of Ask Math Anything. See you.